Hello students, welcome back to JCE Connect series of lectures. So we'll continue module number 4, that is turbines, in that impulse turbines. So in previous lecture we have discussed introduction to turbines, general layout of hydroelectric power plant, heads and efficiencies of turbines, then the classification of turbines. So in this particular session we will be discussing mainly about the Pelton wheel and its working principle and components and velocity triangles. So as we know, the Pelton wheel is a free jet impulse turbine. It is named after American engineer Lester Pelton, and it was invented between 1829 and 1908, and it is a simple and only hydraulic turbine and which operates efficiently uh, and is invariably used for heads in excess of 450 meter, and for a smooth running and good performance are the other common features of this unit. So whatever this picture shows, the Pelton wheel turbine, and the Pelton wheel turbine generally called as a impulse type of a turbine, and the reason for calling this as a impulse type of a turbine, the energy available at the inlet of the turbine is only a kinetic energy, and pressure is atmospheric from inlet to outlet, and it works on the basis of impulse momentum principle, and hence the Pelton wheel is been called as impulse type of turbine. The components of Pelton wheels are uh, this shows the picture of a Pelton wheel. The components of this Pelton wheel are: it has a nozzle and a flow regulating arrangement. So it has a nozzle and flow regulating arrangement. This one, nozzle and a flow regulating arrangement. And the second component is a runner and a bucket. This is the runner. The rotating part of the turbine is called as a runner and bucket arrangement. And the third part, it has casing, and fourth one is a braking jet. And this Pelton wheel is a tangential flow impulsive type of a turbine, and as we know, it is named after L.A. Pelton, an American engineer, and is suitable for high head and low discharge. And this schematic picture shows the Pelton wheel, and the main components of this Pelton wheel are nozzle and flow regulating arrangements, runner and buckets, casing, and braking jet. So we'll discuss one by one. So nozzle and flow regulating arrangement. Um, as we know, the water from the head race comes down along the penstock, and the penstock is nothing but a long pipe, and it enters the nozzle. Means that this is a penstock, and this penstock is been fitted with the nozzle at the end of the pipe. This is the nozzle from where the jet issues and is impinges on the buckets of the Pelton wheel. The change of momentum of the fluid as it changes its direction along the bucket results in rotation of the wheel. Then the flow of nozzle, that is a flow through the of nozzle can be controlled by means of this whatever the water is being flowing through the nozzle, which is been controlling by this uh, uh, by means of an axial moment of sphere. This is a by axial moment of a sphere, or it is called as a needle fixed to the end of the rod. When the speed of the Pelton wheel uh, increases, when the speed of Pelton wheel increases, the sphere is uh, pushed forward into the nozzle, and hence the quantity of water striking the bucket is reduced. When the speed of the wheel falls, the spear is drawn back and it allows a larger quantity of water to pass through the nozzle. So this is the function of this spear, and this is the arrangement. There is nozzle with the flow regulating arrangement. The next is the runner with the buckets. Runner is nothing but a rotating part of the turbine. Here it is been showing. This is the runner, and it is a rotating part of the turbine. And on the runner, on the periphery of the runner, the buckets are being fixed at equidistant, and this shows and this runner is coupled with the shaft, and this is the shape of the bucket. The shape of the bucket is like two spoons. When you join two spoons together, whatever the shape you get, that it looks like that shape, this bucket. And this bucket will be having a common dividing edge. This is shown here. This is a common dividing edge. The incoming jet, whatever the jet is striking to this bucket, the incoming jet of water meets the bucket and at the central edge, and that is called as splitter. When the where the jet strikes at the center of this bucket, this part is called as a splitter, and this splitter divides itself into two parts, and after turning through 160 to 170 degree, and it leaves the jet from its outer edge. It leaves the jet from the outer edges. And the advantages of having two spoons lies uh, lies in the fact that the axial forces, that is forces perpendicular to the direction of motion, which neutralizes each other, being equal and opposite, and hence bearings supporting the wheel shaft, that is this one, the bearings supporting the wheel shaft are not subjected to any axial thrust. And the bottom portion of this bucket is cut off. Look at this figure. The bottom portion of this bucket is been cut off. Here look at this bucket, it is the bottom portion is been cut off here. And look here, the bottom portion is cut off. This is done because the surface of the spoon at these portions, if you take the surface of the spoon at these portions is raised, and water striking at these portions will not be able to turn through 160 to 170 degree, as it is a desired angle required in a Pelton wheel, but instead it will be deflected back, thereby disturbing the incoming bucket. uh, so the water jet after impinging on the buckets is deflected through an angle of 160 to 170 degree instead of 180 degree, so that it uh, may not strike the back of the incoming bucket and retard the motion of the wheel. So that is the reason why this bottom of the bucket is been cut. uh, then next is a casing, and it is made of cast iron or fabricated steel plates. The main function of the casing is to prevent the splashing of water and to discharge the water into the tail race. And it is important to mention here that the casing has no hydraulic function, just it is a safeguard for the turbine. Okay, then next will be the next will be the braking jet, one more component, the braking jet. Here you can see the braking jet will be provided, braking jet. And when the nozzle is completely closed, if this nozzle is completely closed, this one, by uh, pushing the spear in forward direction, or by moving the spear in the forward direction, the amount of striking the runner reduces almost zero. But the runner, due to inertia, even though it has been closed, the nozzle has been closed, because of the inertia, the runner goes on revolving for a long time. This runner goes on revolving long time. To stop this runner in a short time, a small nozzle is being provided which directs the jet of water on the back of the vanes. So which directs the jet of water on the backs of the vanes, and this jet of water is called as braking jet. Okay, so these are the components of Pelton wheel. Next. So this shows the configuration of water flow in a buckets, how the jet is being striking the buckets. This is the just side view of the bucket. You can see the bucket. Actually the bucket will be like this. Then you join the two spoons together, whatever the shape you get, so that in that shape the bucket will be there. And this is the curved spoon shaped buckets, and the rotation is, sorry, so here the runner is coupled with the shaft. So this is the shaft and this is the rotating shaft, and this is the water pressure, and water is striking at the center of the bucket, and it is deflecting. So runner or a Pelton wheel. Next, the basic working principle: when a high speed water jet injected through a nozzle hits buckets of a Pelton wheel, it induces an impulsive force. Hence, this Pelton wheel is been also calling as a impulsive turbine. And the force makes the turbine to rotate, and the rotating shaft runs a generator which is been coupled with the shaft and produces electricity. Pelton turbines transforms kinetic energy of water jet into a rotational energy. In the velocity triangle, how to draw a velocity triangle for this particular Pelton wheel bucket? It is very important to draw a velocity triangle. Velocity triangle helps us to calculate the force exerting by the jet, and also the work done by the jet, or the power of the jet can be easily calculated through the velocity triangle. And this velocity triangle can be drawn at the splitter and at outlet velocity triangle uh, of the bucket. Uh, so this figure shows how the velocity triangle can be drawn for the Pelton wheel bucket, and this is the this shows the side view of the bucket. So this is a side view of the bucket. Means how to draw the velocity triangle for the Pelton wheel. So this picture shows how the jet is being striking the blades of the bucket, uh, as the water energy is being that is, the water is applying a force on the buckets, and the force is being transferring from the bucket to the runner, and runner to the shaft, and shaft to the generator. And this figure shows the shape of the veins or the buckets here, the shape of the vein or a bucket of the Pelton wheel, and the jet of water from the nozzle. Here you can see the jet of water from the nozzle strikes the bucket tangentially. It strikes the bucket tangentially, but at it strikes at the splitter exactly at the center. So this is actually it strikes the jet at the splitter. This is a splitter which splits the jet into two parts. So after striking the one, it splits into two parts. The water will glides over the surface and it exits like this. Um, these parts of the jet glides over the inner surface and comes out at the outer edge. It comes out at the outer edge, and this uh, that is this figure shows how the jet is being uh, striking the bucket and how it is going out. It shows, which is been showing by drawing a velocity triangle. The inlet velocity triangle is drawn at the splitter, and the outlet velocity triangle is being drawn at the outer edge of the bucket. And this velocity triangle is been drawn by the same method as we studied previously. Since the jet is striking, just look at this figure. Since the jet is striking tangentially, so, and that too at the center, hence the inlet velocity triangle will be straight line. So on this straight line only you can mark the absolute velocity, and you can mark uh, here it shows that v1 shows the absolute velocity, and u1 is the direction, the velocity of the vane. It is velocity of this vane moving in forward direction, and vr1 shows the relative velocity, and vw1 will be the whirl velocity, and the flow velocity in that inlet will be 0 here for the Pelton wheel. And it, just you look at the outlet velocity triangle, and it will be having a vr2, v2, and vf2, all components of velocity will be there. Okay, so you know how to draw this velocity triangle. We have explained and earlier. So just to remember the drawing up a velocity triangle for a Pelton wheel bucket, and this triangle will be using to calculate the force exerting by the jet, and also for the calculation purpose. I hope you understood this one. So in next uh, class, will derive the equation, that is work done for a Pelton wheel by utilizing this velocity triangle. So this is very important, and try to understand how the jet is coming and hitting the blade, and how it is exiting. Okay, and here it is being shown the angle of deflection also, and the jet is hitting at the center of the bucket, that is at splitter. And why the name is splitter, it splits into two parts. The jet is being splitting into two parts, and having the same magnitude both the side, then it exits. Okay, I hope you understood this one. Thank you.